we are fortunately to have Argyrios and Deligkas. You are Greek, right? I see your name.
Yes.
Yeah, and a little bit of Greek. I see. Okay, good. Yeah, great. Welcome, Dr. Deligkas. He's coming to give us a paper on the 1/3 approximate Nash equilibrium in Bimatrix game. It's a progress over like 13 years since 15 years. Yeah, I remember it's 15 years of post seminar work. So let's Paul is also here. We are fortunate to have Paul here, and let's hear today's talk. Welcome.
Thank you. Thanks for the invitation. Thanks, Xiaotie. Thanks, Hanyu. I just want to say that with Xiaotie, we have met in 3 or 4 different continents. So Xiaotie was in Liverpool. We met in a conference in China. We met in a conference in Canada, and we even met while I was in Israel. So it's good to see you again, even online. So today I'm gonna talk about a recent result that we have with Michael Vasoulakis, who is a postdoc in Greece, in Crete, and Vangelis Markakis, who is in Athens. So if you have any questions at any point, feel free to interrupt me, so I can answer on the fly. So what is this talk about? Bimatrix Games, as you might know, is the games played between 2 players that we will call them the row player and the column player. And these games are defined by a pair of payoff matrices. And we will use R to denote the payoff matrix for the row player and C, the payoff matrix for the column player. And we assume that these matrices have n rows and 10 columns. So this is a bimatrix game with 3 strategies per player. And for every pair of actions or combinations, we have to define the payoffs of for each player. In order to play the game, each player chooses a probability distribution over the set of actions. So the row player chooses a probability distribution X over the set of rows, while the column player chooses a probability distribution Y over the set of columns. And in a play, each player gets an expected payoff, and they are given by these formulas. So it is the expectation, essentially what over the possible outcomes times the utility, the payoff each player gets for each outcome. And for notation simplicity, we will use this R x, y and C x, y to denote the expected payoff of each player. Crucially, in bimatrix games, the payoffs of the players depend both on the strategy they choose and the strategy their opponent chooses. So if the row player chooses top and the column player chooses middle, then this will be the outcome of the game, and the row player will get payoff 1/2, while the column player will get payoff 1/3. Another notion that will be of interest to us is the regret. The regret of a player is the difference of the maximum a player could get given the strategy of their opponent minus what they actually get. So in this case, we can see that the row player gets 1/2 under this play, and the maximum is 1. So his regret is 1/2, and the column player gets 1/3, while the maximum he can get is 1, so his regret is 2/3. Okay, and we will use these notions to denote the regret of the players. So this is the game, but what are we looking for? We are looking for an epsilon Nash equilibrium. What is an epsilon Nash equilibrium? An epsilon Nash equilibrium is a strategy profile, so one strategy for the row player and one strategy for the column player, such that the maximum regret of both players is at most epsilon. Okay. So, any questions so far? What is the epsilon Nash equilibrium problem? It is very simple. Given an n times n Bimatrix game, compute an epsilon Nash equilibrium. Why is this of interest? Because Nash equilibria correspond to stable outcomes of the game. But okay, for which epsilons does this problem make sense? Luckily, it makes sense for every epsilon greater than 0, because Nash's theorem states that every game possesses a 0 Nash equilibrium, an exact Nash equilibrium. So our goal is to find an epsilon Nash equilibrium with the smallest possible epsilon, since we know that for every epsilon greater than 0 or equal to 0, an epsilon Nash equilibrium exists. Okay. So, what's the story so far? How this problem? What is the current state of the problem? So observe that first of all, let me say that since we assume that the payoffs are in 0 and 1, in 0, 1, the epsilons that we will be concerned that are of interest are in the range of between 0 and 1. So in a groundbreaking, in a set of groundbreaking results, Chen, Denk, and Tenk, and Daskalakis, Goldberg, and Papadimitriou proved that the problem, the epsilon Nash problem, is simply hard when epsilon is an inverse polynomial in M. So here, what does this mean? It means that for epsilon smaller than this value, we cannot hope to find an epsilon Nash equilibrium fast in polynomial time in N. So it is believed that for this small epsilon, we would need exponential time in N with respect to the number of strategies per player or to the input size of the game in order to find such an epsilon Nash equilibrium. On the positive side, Lipton, Markakis, and Mehta derived a quasi-polynomial approximation scheme that says that for every epsilon, we can find an epsilon Nash equilibrium in this time. Okay, so essentially, if epsilon is 1 over poly of n, the problem is hard. If epsilon is constant, we can find it in quasi-polynomial time. The problem is solved, right? No, because quasi-polynomial, although it is a great improvement with respect to exponential time, it is still not polynomial time. So what we will care is we want to find an epsilon Nash equilibrium in polynomial time with respect to n, so to the size of the game. And after these two breakthrough results, the quest for the smallest possible epsilon has started. And the first result found that for epsilon 0.075 by Kodogiannis, Panagopoulou, and Spirakis, this is we can find such an epsilon Nash equilibrium. So this is easy. And then there were two results by Daskalakis, Mechta, and Papadimitriou that they derived a simple algorithm to find a half Nash equilibrium, and another a bit more complicated algorithm to find a 3-8-2 Nash equilibrium, which was followed by a different algorithm by Bose, Birka, and Markakis. And finally, the TS algorithm, or Tsaknakis and Spirakis algorithm, that moved the bound to 0.3393. So all these results here appeared in a period of 3 years. And later, Rubinstein proved that there exists a small but constant epsilon star, such that below this epsilon, we need quasi-polynomial time to find an epsilon Nash equilibrium, assuming that the complexity class PPAD requires exponential time. So this is a conditional result, assuming the exponential time hypothesis for PPAD. So, as I said, all these results, with the exception of the last result of Rubinstein, happened between 2004 and 2007. And the state-of-the-art, the Tsaknakis and Spirakis algorithm, was derived in 2007. And we thought, okay, in practice, this algorithm works very, very well. I mean, if you try to and use this algorithm, the epsilon that you will find is usually 0.004 or something like that. With Rahul and John Fernley and Tobena Peter Igwe, we had an experimental paper, and TS algorithm was always spot on, was always finding a very, very good approximation of a very, very good epsilon. So we were wondering, okay, possibly this 3393 is not the correct answer for a TS algorithm, and maybe a better analysis is possible, because after all, okay, why 3393? This number is not a well-behaved number, an intuitive number. Maybe, so many people thought that maybe, okay, maybe we can perform a more clever analysis for the TS algorithm and lower this bound. Apparently, this is not possible, because as people from Beijing and many people from this call proved that, in fact, the analysis of TS is actually tight. So Tsaknakis and Spirakis maxed out their technique, did the best they could do. They didn't miss a thing. So this was the answer for their algorithm. And no hope, there was no hope that we could improve it directly. So, and around that time, I said to Michalis Vasoulakis, okay, trying to improve TS is impossible, but there is no hope. But Michalis said, no, come on, it is possible. And in fact, what he came up with a modification with a new algorithm that I will call this DFM algorithm, that achieves a one-third Nash equilibrium in polynomial time. And this is the result of our paper. So at a very, very high level, our algorithm works as follows: uses the TS algorithm as a basis, and then we modify what I'm going to call the second phase of TS in order to get a better approximation. And in what follows, I will first explain how Tsagnakis and Spirakis algorithm works, and then I'll try to explain how we modified this second phase of TS in order to achieve the one-third approximation. So let us begin with the Tsagnakis and Spirakis algorithm. And recall that what is our goal? Our goal is to find an epsilon Nash equilibrium, which is a pair of strategies x, y, such that the maximum regret is less than epsilon. So what Paul with Tsagnakis did, said, okay, let's define this function that captures essentially the maximum regret a player gets. And by definition, when this value, the value of this function is less than epsilon, then the strategy profile is an epsilon Nash equilibrium. And what they said, okay, let's try to minimize this function. And what optimization people do when they want to minimize a function? Perform gradient descent. Okay, so at a very, very high level, TS algorithm first performs gradient descent on this function g, and this is the phase one. So when it reaches a stationary point, it can use the stationarity conditions in order to bound the value of g. And apparently, the stationarity conditions and the stationary point of this function is not good enough in order to achieve the 33.3393 approximation. So they need a second phase where they construct some extra strategies, and they prove that either the stationary point or the extra strategies provide a good approximation. By good, I mean 0.3393. So our algorithm essentially will modify phase two. So let's see in more detail how both phases of TS, and I'll try to explain and give some intuition what's going on. So in the descent phase of TS, several different procedures are used. So the regret equalization procedure, and the first thing is the regret equalization. This is crucial. It is this essentially, you do not have to pay attention on what it is written here in the maths, but essentially what the regret equalization does is takes a strategy profile where the two players might have different regrets, and it equalizes them such that it outputs a strategy profile where the regrets of both players are equal. This is crucial in the analysis, in fact, and we have used it in both Tsagnakis and Spirakis, and we used it in order to evaluate the approximation guarantee of our algorithm. And then in the core of the gradient descent is this linear program that we call it the primal linear program. So for every strategy profile, it formulates this linear program where here x and y are fixed, and the variables are gamma, x prime, and y prime. What is gamma? Gamma essentially here corresponds to the gradient at point x, y when we move towards the direction specified by x prime and y prime. So this linear program computes the steepest direction to move from x, y. Now, why this works? Tsaknakis and Spirakis did loads of calculations in order to derive this, and yes, and believe me that this works, and it did compute direction that it is the steepest. If you move there, it is your function, the function g is decreased with the highest rate. And as I said, the regret equalization was crucial in the analysis, but I haven't specified yet the descent procedure. The descent procedure works as follows. It starts, first it computes, it equalizes the regrets of the two players. Then it solves the primal LP to compute x prime, y prime, and gamma, and then checks this condition. But this condition essentially checks if the point that we have found is a stationary point, and because we are in the discrete world, we do not have infinite precision, we check against the constant delta, and if this condition holds, we have a delta stationary point. If we are not in a delta stationary point, we use the directions that we found by solving the primal linear program, and we move in a predefined way towards this direction. So what it is written here essentially simulates gradient descent for this function g that is non-differentiable. All right. What it is crucial, the crucial thing is that this phase, the descent phase, converges to a delta stationary point in time polynomial in n and 1 over delta. So roughly, after 1 over delta square iterations of this, we will converge, we will find a delta stationary point for G. So we found a stationary point. What now? As I said earlier, using just the stationarity conditions, so if you can see here, we can use the value of gamma and the delta in order to bound the value of G, which gives us the approximation for this strategy profile. So, but as I said before, using just the stationarity conditions is not good enough for the purposes. It's not good enough in order to achieve something good, a good approximation. It's not terrible, but it's not that good. So in order to achieve a better approximation, the TS algorithm proceeds to phase 2, which is the strategy construction phase. The strategy construction phase, it utilizes, again, the primal linear program and its dual. So it computes using the dual linear program. It computes the so-called dual strategies a pair of strategies, one for the row player and one of the column player, that are derived by this dual linear program, and that these strategies have some properties. And the property is that the strategy that is computed for the row player is a best response against the stationary strategy for the column player, and the dual strategy for the column player is a best response against the stationary strategy of the row player. Okay. So it computed. So right now we have the stationary strategies X and Y, and we have the dual strategies W and Z. What next? Next is the actual strategy construction phase. And in order to define the strategies, in order to decide what strategies to output, Tsaknakis and Spirakis defined two quantities, these lambda and nu quantities. And according to the values of lambda and nu, they decided how to proceed and what to return. So lambda and nu, by definition, are between 0 and 1, and depending on the values of lambda and nu, they would return different strategy profiles. So you can see here that in the first three cases, they output one specific strategy profile, and in cases 4 and 5, they choose between the best between two strategy profiles. And here, someone would say, okay, how did they choose how to balance between the primal strategy and the dual strategy? This is a convex combination that essentially equalizes the regrets of two players under this strategy profile. What is interesting, though, is that the first three steps of the TS algorithm output a 1/3 Nash equilibrium. And it is the last two steps is where the algorithm needs to go above 1/3. And these two steps are, let's call them the bad steps, that achieve each one of them outputs a 0.3393 Nash equilibrium. So what did we do? We replaced steps 4 and 5. So our algorithm uses, it is identical up to step 3 of TS, and then we replaced steps 4 and 5 in order to achieve a better approximation. So what did we do? We replaced step 4 with that, and step 5 with this. And we were done. So, by the way, even here, step 4 and 5 are symmetric, and in our case, step 4 and step 5 are symmetric. So let me try and give you and provide some intuition about how the new modified steps work. So recall from the TS that the cases of interest are when lambda, that when these variables, with these quantities, lambda and nu, are one of them is between 1/2 and 2/3, and the other one is above 2/3. So we will focus on this case where lambda is above 1/2, between 1/2 and 2/3, and mu is above 2/3. So what did we do? The first thing that we did is we defined some new strategies. We defined some extra strategies. So we defined this strategy y hat, which is which equiprobably mixes between the stationary strategy and the dual strategy for the column player. And we have computed a best response against this new strategy that we call this strategy W hat. And in addition to this, we have defined, since now we have more strategies to play with, we defined more parameters in order to choose what to output when, and these parameters essentially helped us in the analysis. So we have augmented what TS was doing with an extra level of, someone would say, complexity in order to perform a better analysis. So using these new strategies and new parameters, we have identified two subcases. Sorry, yes? Is there a question? Okay. Someone has their mic on, by the way. So using the values of these parameters, we have identified two different cases, and in each case we were outputting two different pairs of strategies. So we were outputting the best of two pairs of strategies. As before, we were utilizing the stationary strategy profile and a different strategy profile that uses the dual strategies W and Z plus the new strategies either W hat or Y hat, depending on the case. Again, the convex combination here, how these values of P and Q are chosen in such a way that in this strategy profile and in that strategy profile, the regrets of the players are equal. And performing an analysis, we saw that at least one of them will be a 1/3 Nash equilibrium. So subcase 4.1 was associated with one lemma where we saw that if these conditions are satisfied, then one of the two strategy profiles is a 1/3 Nash equilibrium. This was a page long, the proof of that lemma, and then case 4.2 was associated with three subcases. For the values of our parameters, and for each subcase was associated with a lemma. This was half page, this was one of the half page, this was 1 page. And I have to say that in the last equation of the last lemma, we had a bug. That luckily for us, Hangyu found it out, and luckily for us, this was an easy fix, a one-line fix, 15 minutes of me cursing, but Michalis found the solution. And in the end, by performing some technical calculations using all all these constraints, we can prove that one of these, in every case, in every step, in every subcase, the algorithm outputs 1/3 Nash equilibrium. Now someone would ask, okay, can we do any better? Interestingly, these two cases work only when the values of lambda and nu are in the specific ranges. For me, it was magic, right? If lambda was it was 2/3 plus a tiny quantity, then these two cases would fail. Of course, the previous steps of TS would fail. So this is the complete algorithm. So if we had less than, if we had different ranges for lambda and nu, the first three steps would not work properly. But nevertheless, even if they worked, our analysis wouldn't work because these two cases would fail. So this is the algorithm. And the theorem states, as I said, that this algorithm computes 1/3 Nash equilibrium. So yes, we managed to find the polynomial time algorithm for 1/3 approximate Nash equilibria for two-person games. And then I thought, okay, so the talk is already technical. Shall I prove some of these lemmas? And I said, okay, no. Instead of that, I will talk about a new result, which, as you can see, only the middle line changes. And this is a new result for a different approximation of Nash equilibrium, well-supported Nash equilibria. So what is an epsilon well-supported Nash equilibrium problem? This time, instead of an epsilon Nash, we are looking for an epsilon well-supported Nash equilibrium. And what is that? Again, this is a pair of strategies, X and Y, such that every player plays with positive probability only pure strategies that are within epsilon of being best response, that they achieve epsilon less, at most epsilon less than the maximum payoff achieved by any best response. So this is a more strict notion of approximation. So you can think of it as an ex post guarantee that any pure action that you are playing, it is not that bad an expectation. While epsilon Nash equilibria allows us to put a positive probability on arbitrarily bad strategies. And an epsilon well-supported Nash equilibrium is an epsilon Nash equilibrium, but the other direction does not always hold. So this was the story for epsilon Nash. What about well-supported? So for well-supported, since it's a stricter, a more difficult notion of approximation, we expect worse results. Let me say first that the results of Chen, Denk, and Denk, and Deligkas, Goldberg, and Papadimitriou, for the PPED completeness hold for well-supported Nash equilibria as well, and the quasi-polynomial lower bound of Rubinstein holds for well-supported Nash equilibria as well. So again, Paul Spirakis is involved in well-supported Nash equilibria as well. So the first result was by Kodogiannis and Spirakis, and they achieved a an epsilon of 2/3, and then this was significantly improved by Fernley, Goldberg, Savani, and Sorensen to 66.6608, and then this was followed by another significant improvement by Jumai, myself, Fasoulakis, John Fernley, Marcin Zurzinski, and Rahul Savani to 0.6528. And while we were waiting for the replies from Mesa for the previous result for the 1/3 Nash equilibrium, Michalis Fasoulakis said, "Okay, guys, I think we can get 1/2 well-supported Nash equilibrium in polynomial time." And I said, "No way, there is a bug." But then Michalis showed me the proof, and we managed to improve the bound from this 0.65 to 1/2. And the algorithm, this is the whole algorithm. It might look a bit intimidating, but I would argue that the algorithm is intuitive, and it has the analysis is simple, and in fact we can convert it to a query efficient protocol that finds a 1/2 Nash equilibrium, a well-supported Nash equilibrium with n log n queries. So this is the crux of the algorithm, this step 3, and I don't want to get into details because I understand that up until now the talk was really technical, but I just wanted to say and put these results in context that okay, there was another improvement for a different notion of approximation, and usually the people that study the one notion are aware of the other, and I thought that it would make sense to just present these to say about these new results. So what's the future? I mean, you can see the figures here. The gaps are indeed huge, and by the way, the gaps are scaled versions. This is indeed the middle of this line, and this is indeed the 1/3 of the line. Maybe this epsilon star would be much closer to 0. But what I want to argue is that our understanding for both problems is far from satisfying. The gaps are huge. In addition to this, what I see is that the algorithm that the gradient descent approach reached its limit. Paul with Chaknakis did an awesome work and created the basis for good approximations, and we managed I think we managed to push it to its limit. In order to go beyond 1/3, we would either need if we use the stationary points of this function, we would need a completely different analysis because all the steps fail. So none of the steps works for below 1/3. And for well-supported Nash equilibria, I didn't go into details, but I would say that more or less every paper so far used in one way or another zero-sum games. So we need a different approach, some new algorithms with new algorithmic techniques in order to close these gaps. I'm not implying that these gaps will match Aviad's lower bound. I think the answer should be somewhere in the middle, but in any case, we need new algorithmic results in order to push lower the upper bounds, and stronger lower bounds, better understanding of the PCP for PPAD in order to push this epsilon star. This epsilon star is, the theorem states, there exists some constant epsilon star such that epsilon Nash requires quasi-polynomial time. So to push it to what I like to call a real constant, a constant that we can actually write down and say that, okay, this is the bound. There is some progress with respect to tight results for many player games. So we derived some results, some tight results for well-supported Nash equilibria for Polymatrix games. We derived some tight results for graphical games, but the most fundamental games that are two-player games are far from being understood. And I want to say that we definitely need more results here. And on that bombshell, I want to thank you. I hope you enjoyed it. Any questions?
Yeah, I have a,
Okay, go ahead, please. Yeah.
I have a technical questions on epsilon Nash algorithm. So, how do you choose hat y hat? Why do you mix them with 1/2 other than other coefficients?
Okay. Here, essentially, the 1/2 does not really make the difference.
Oh, so it's arbitrarily chosen.
Sorry. Okay. In fact, okay. Well, okay. Let me state the following. We could parameterize instead of 1/2. We could parameterize it in a different way. We need a convex combination between the stationary and the dual strategy. But for any different convex combination of these two strategies, we would change this parameter P. So this parameter P and Q, these two parameters would change with respect to what we had here between YS and the stationary and the dual. What it is, we chose to write it like that in order to make it friendly for the reader and have an intuitive meaning for y hat.
Okay.
Does this answer your question?
I think I got some ideas.
Okay. Well, I'm happy to discuss.
So, in fact, we recently studied the tightness of your algorithm. So in fact, we proved that 1/3 is tight in the 4 cases, and in the last case, although lambda and mu cannot attain the 1/3, since you require mu is strictly greater than 2/3 rather than equal to 2/3. So the 4th case, we cannot require the algorithm to reach exactly 1/3, but we can reach 1/3 minus epsilon with arbitrary small epsilon.
Nice. Actually, yes, I forgot to mention that. Yeah, this was one question that I was about to ask. Our guess was that indeed this is by extending your approach that we would get someone could get a 1/3 matching bound. But yeah, this is great news in the sense that look, we need new algorithms, right? We need new ideas.
Yes.
Any other questions? I saw Paul being ready to ask something.
No, I didn't want to ask anything. It's a nice talk. I just wanted to say that it's a pity that Tsagnakis is not in life anymore. To be able to, he left left us about 2 years ago. So yeah, and in the beginning of the pandemic. Yeah, but very nice talk, and I agree with you, Argyrios, that we need now new ideas to go below 1/3 if possible. Yes.
Any other questions or comments?
Argyrios, for the 1/2 lower bound for the well-supported equilibrium and this 1/3 approximation algorithm, how do you compare them, like in the real cases, like say for in simulation?
We haven't done any simulations yet for any of them. We haven't done any simulations for any of them, but actually, this is well. What I wanted to say is that for this algorithm, for the 1/2 well-supported Nash equilibrium, we don't know if the algorithm is tight. We have some thoughts that we cannot improve the analysis. Some cases fail. But we do not have a tight result. And in fact, what I wanted to say is that this algorithm might has some space for improvement. I'm not saying that it's going to be easy, but there is some space. But here, what type of empirical analysis do you have in your mind?
I was looking at they are going into on different metrics in terms of approximation. But in practically, we know TSR algorithm is very well performed And how is the case for well-supported Nash equilibrium, those approximation algorithms?
Okay. What I can say about, if I understand correctly, the question is, what if the games have some structure and they come from a real life problem? The answer is that we don't know. We don't know. Well, what I didn't say is that for epsilon Nash, if all the payoffs are either 0 or 1, the original TS algorithm gives a 1/4 approximation. We cannot beat it. Our algorithm cannot beat it. And although we thought about more special classes of games like symmetric games and win-lose games, our algorithm does not immediately give anything better here for 1/2. This is unexplored territory. Traditionally, they seem easier, but we didn't actually we didn't manage to get anything improved here. But I agree with you that real life problems make sense, and we should study them a bit more carefully.
Yeah, I have a student like worked on like a lot of implementations. Maybe one hand, are you here? Okay, yeah. But
I'm happy to discuss offline or in a different call about this. Yes.
Okay, maybe we can discuss it next time. We'll
Yes.
make
Yes.
Yeah. Okay. Any other question? Let's maybe there's no more question. Let's thank Argyrios again.
Thank you. Thanks for the invitation.
Yeah. Hope to see you again. Okay.
Take care. Nice to see you.
Yeah. Hi, Paul. Bye. Hope to see you again.
Bye. Good to see you.
Yeah. And also Rahul. Bye.
Yeah, hi and bye, Xiaoqiu. Nice to see you.
Yeah. I see you. Good to see you.
Bye.
Yeah. Great. Yeah. Bye.